Hello and welcome to my YouTube channel. My name is Maarten Hart. In this video I will teach you how to make an optimal geodesic grid. A geodesic grid is a grid that measures a sphere into polygons, usually triangles or squares. This will be a step-by-step tutorial explaining how to mathematically construct the grid. I have developed this grid myself and I managed to get a paper published in 2022 in the Journal of Computational Physics. The paper contains all the information I present in this video, plus a lot more information that we don't need to construct it, such as why it is an improvement compared to existing geodesic grids. In this video I'll focus on gridding the surface of a sphere, also known as a two-sphere. The paper goes one step further, explaining how to grid a filled sphere using tetrahedrons of near equal volume. I won't focus on that now, but maybe I'll do that in a later video. Now you may wonder, in what way is this new grid better than existing grids? Because we already have many ways to represent the Earth as a flat map. Each projection has its own pros and cons and purposes. It is never possible to create a flat map from a sphere without doing some concessions. Let me show you. Here I have 4 well-known examples, each with their own goal and each with their best performance and their own concessions. If you do not care about the north orientation and just want a map that is as correct as possible in both area and shape, even at the poles, then this is probably the grid you want. When is that useful? Well, mostly for simulators in meteorology and geophysics, but also if you want to have a seamless spherical map in computer graphics. These are the 5 platonic solids. These are the only regular polyhedrons. This is the closest you can get to a sphere made of polygons that are all identical. You cannot go any further without doing concessions. We are going to use the icosahedron because of these 5 that one is the closest approximation to a sphere. We will fit this icosahedron in a sphere and use it to cut the sphere into spherical triangles. Now this concept isn't new. In 1985 Dr. John Baumgartner published a grid where he used the icosahedron as a base. Then he just cut every rib into 2 and connected the dots. When you do this over and over again, you get a finer grid, each time multiplying the amount of triangles by 4. This already gives a very good grid. With that grid, the largest triangle is only 20% bigger than the average triangle. But we can do better. We can reduce this deviation to 0.4%. Now there are already ways to optimize the bisecting grid into a better grid using very complex iterations, but you can now do this directly in a relatively easy way. Here we go. We are going to use a sphere with a radius of 1. This is also known as a unit sphere. Inside we are going to fit an icosahedron, and we take one triangle and we orient it like this. These are the 2 main views we are going to use, the front view and the top view. When we look at the front view, we'll draw a vertical line from the left point. From this perspective, the cut on the right is a straight line. We'll extend that line. Where the 2 lines intersect, we have a point which we will call the projection point P. This will be the point from where all the magic happens. From point P we will draw a line through the midpoints of the side of the triangle. If we cut it like this, from this specific projection point, we'll get a new smaller triangle, which has almost exactly 1/4 of the area of the original triangle. Next, we rotate this new cut in the top view 120 degrees. This will give us 4 triangles with almost exactly the same area. The new cut will have a new midpoint, which we can cut again. Of this new cut, we take the lowest point and rotate it to 120 degrees. We cut that point as well. Each new cut has a new midpoint, and we can keep repeating the process, doubling the amount of cuts each iteration, and this quadruples the amount of triangles each iteration. Before we go into more detail, we need some basic knowledge about operators. I'll assume you know these basic operators and how they work. But we are not only going to use numbers, we are also going to use vectors and coordinates. Vectors and coordinates are basically the same thing. I mean, vectors and coordinates both have 3 values. These values are an x component, a y component and a z component. A coordinate represents a position in 3D space. That's just the point. A vector can be seen as a direction in 3D space. That's more like an arrow. For the rest, mathematically there will not be a difference between vectors and coordinates in the way we'll use them. A special type of vector is the unit vector. A unit vector is a vector with length 1, and we show this as a letter with a little hat on it. Unit vectors are super convenient for calculations in 3D space, and we are going to use this a lot. Also note that a unit vector is the same as a coordinate on our unit sphere. Now for these operators, let's see what happens when we put in a coordinate instead of a number. We can add vectors together, we can subtract them, we can multiply vectors by some value, and we can divide them by some value. For example, when we subtract a coordinate from another, we get a vector which is an arrow pointing from one coordinate to the other. And when we multiply a vector, we can scale it up. Here are some examples. And pause if you like to get a better understanding of it. But for vectors, there are more operators. We are going to use these 4 and I'll explain how they work. We use it in a way of vector dot vector, and as an answer we get a number. This is mostly used to calculate the distance from a point to a plane. Next is the magnitude. The input is a single coordinate and the output is a single value. This value is either the length of a vector or the distance of a coordinate to the origin of the coordinate system. Next is the unit vector. I've mentioned this one before. We give the vector a hat on top to say we use a vector with a length of 1. Last is the cross product. We input 2 vectors and we get a new vector. This new vector is perpendicular to both vectors of the input. Now let's see how they work. The dot product works by multiplying the x components of both vectors, then the y components, then the z components, and we just add them all up. The magnitude operator is a 3D version of the Pythagorean theorem. We square the components, add them up, and take the square root of that. We can get a unit vector by taking a vector and divide it by its own magnitude. This makes sense. If you have a vector of a length of 3 and divide it by 3, you get a vector with a length of 1. It's as simple as that. Probably the hardest one is the cross product. Let's break it down. The input is 2 vectors and the output is a new vector. For the x component of the output, we need the y and z components of the vectors. Y times z minus z times y. For the y component, we need the x and the z components of the vectors. Z times x minus x times z. And for the z component, we need the x and the y components of the vectors. X times y minus y times x. If this is the first time you see this, it may seem hard. But if you use them often, you'll get used to it. And eventually it will make your math easier. For example, if we want to have the distance between 2 points, this is how we write that down. It's the magnitude of coordinate A minus coordinate B. Compare that to how we would need to write it down without these operators. 2 more things before we go. I'll explain how we define lines and planes. This seems obvious, but there are multiple ways to describe a line and a plane mathematically, and I will use a very specific way to describe them. Here we have a line from A to B. This line has a vector, which is an arrow, pointing from A to B. What I will use to describe the line is its unit vector, that's an arrow in which direction it is pointing, and a point on that line. We will use the point on the line that is the nearest to the origin, and this will be very convenient later. The vector is just the unit vector from B minus A. Then we calculate the nearest point to the origin. What this function says is the point minus the direction scaled by some distance, and that distance is the distance you need to get as near to the origin as possible. We will also use a specific form to describe a plane. What we need is the distance the plane is from the origin and the vector that is perpendicular to the plane. A perpendicular vector in 3D is called a normal vector. For example, we can calculate a plane from a 3-dimensional triangle. We use the 3 coordinates of the triangle, and first we calculate the normal vector. We need the vector from A to B, and we need the vector from C to A. Then we will use the cross product, and out comes the normal. We'll then use its unit vector, and so now we have the unit normal vector of the plane. Every rib of the triangle is perpendicular to this vector. Now we'll calculate the distance from the plane to the origin. To do that, we take the dot product of any point on the plane. Here's a summary of all the basic operators we will use. Let's now construct the base points of the grid. The easy ones are the origin, which is located at 0, 0, 0, and the top, which is located at 0, 0, 1. Now what we need is the length of a rib of the triangle. This is an equilateral triangle, so all the ribs are of the same length. Well, this is the length we need, and I just got that from a source. Using this length, we can calculate all other values and base points. We calculate the height of the triangle, then we calculate x component of point A, which is minus 2/3 of the height, and the x component of point B is 1/3 of that height. The y component of point A is 0, and since point A is 1 away from the origin, we can use the Pythagorean theorem to calculate the z component of point A. Point B has the same z component as point A, again 1 away from the origin, and the Pythagorean theorem to calculate the final component of point B. This shows how convenient it is to use a unit sphere. We can find point C by using point B, set the y component to 0 and take the unit vector. Point M is the unit vector of the midpoint between A and B. We get the x and z components of point P by multiplying point B with minus 2, but we need to set the y component of point P to 0. We need one more value, and that is the secondary radius of this ellipse. We know the primary radius is 1, and we are going to call the other one r. Why is this an ellipse? Because the spherical triangle has 3 arcs, each is a part of a circle with a radius of 1, but we are looking at it from the side while the circle is tilted. That's why it's an ellipse from this perspective. Let's find out how much the circle is tilted so that we can get the secondary radius. When we look at the icosahedron exactly from the top of a point, we can see that there are 5 equally sized triangles surrounding it. So the tilt angle is half of one of these triangles. This is an angle of 36 degrees because it is a tenth of the entire 360 degrees. What we need is the cosine. We can also write it in radians, but in fact we don't even need to use the cosine because the answer happens to be exactly equal to 1 plus the square root of 5 all over 4. So let's use that. Now we have all the base points and values we need. As said, we will cut the spherical triangles using slices. These slices are planes. Each plane has point P on it and looks like a line from this front view. We just need one more point for each slicing plane to define it. Let's call these slice points. For our first slicing plane, the slice point is point M. If we have a slice point, we can calculate 2 new slice points. Thus, every cycle we go through this process, we double the amount of slices and we quadruple the amount of triangles. We call the input slice point C point Q. So our first point is point M, and we will calculate 2 new target points, point C0 and C1. A way to do this is to construct a plane using point P and point Q. Find the point on the plane where it intersects the top of the unit sphere. So the intersection point with the top arc. We rotate this point in top view 120 degrees and we construct a new slicing plane. Then we find the intersection point with the side arc. That's the elliptical arc in this view. That point is C0. To find point C1, we just need to find the other point on the side arc with the same z value. We can find it by top rotating the point 120 degrees. These are 3D operations, but it can be done entirely in 2D. We need 4 tricks. Remember that from this view we will use the x and the z value, so we won't be using the y value. So to start, use point M and set its y value to 0. Now let's get to those tricks. The first trick is to create a line and find a point that is 1 away from the origin. If a line intersects the unit sphere, it will intersect it at 2 points. We need the point that has a positive z value. Our seed point is point S, and we need to know target point T. Construct a line from point P to S. So we have its unit vector v and the nearest point to the origin n, as explained earlier. The distance from point n to the origin d is the magnitude of point n. We need distance g. This distance is the square root of 1 minus d squared. The target point is point n, plus the unit vector of the line, scaled by distance g. We can substitute in for d and for g. And now we have a simple formula to find point T based on point S. The second trick is that we can simplify the top rotation. Every time we use the top rotation in this process, we will be rotating a point from the middle line. That point will be 2/3 away from the center and we will end up 1/3 away from the center in the other direction. Thus, while the rotation formula is a little bit complex for the entire coordinate, we can remove the y component in the front view, and when we do that, we see that it's just the x component gets negative and divided by 2. The third trick is that we can scale out our ellipse to turn it into a circle. To do this, we need the ellipse radius r we calculated earlier. Point A will remain the same in the scaled version, but point G starts at a magnitude of r and will scale out to a magnitude of 1. To stretch any point Q, we must scale A by the dot product of Q and A, and scale H by the dot product of H and Q divided by the radius r. To unstretch any point Q, we must scale A by the dot product of Q and A, and scale H by the dot product of H and Q multiplied by the radius r. The fourth trick relies on the stretching. When we have stretched everything, we can draw a line from the stretched M to the origin. To get a second point, we can mirror our point along that line. Let's call our stretched M S and the point perpendicular to that T. Here's how we get those points. We already explained how to calculate these points. Now if we have a point A, we know the distance in S direction is S dot A, and in T direction is T dot A. All we have to do to get point B is flip the vector in T direction. To flip a vector, just multiply it by -1. So to get point B, we have S multiplied by S dot A minus T multiplied by T dot A. Now that we have those tricks, let's apply them. Create a line from P to Q. Find point 1 away from the origin on that line. Multiply the x component by -1/2. Stretch the point. Create a line from stretch P to the stretched point. Find the point on that line 1 away from the origin and unstretch that point. To get the second point, stretch point C0 and mirror the point and unstretch it. We can do both at the same time to get both points at once. So here's a summary of the steps. Great, now we have the slicing points. The order of the slicing points may seem a little bit chaotic, and there definitely is a pattern, but for now you don't need to understand that pattern. If I would ever make a second video, I will cover this. But the easiest thing to do for now is to sort the point by their x components. Of course, we are not cutting by slicing points, we need planes. To construct a plane out of a slicing point, just create a triangle. The first point is always point P, the second point is the slicing point, and the third point is the slicing point with y value set to 1. and we already explained how to construct a plane out of a triangle. Nice, so now we need to calculate the grid points. To do so, rotate the slicing planes 120 degrees in top view. As said, the plane consists of a vector, which is its normal, and a distance to the origin. All we have to do is to rotate the vector. Here's the formula to do so. Let's break it down. The new x component is the square root of 3 over 4 multiplied by the old y component minus the old x component divided by 2. The new y component is minus the square root of 3 over 4 multiplied by the old x component minus the old y component divided by 2. The z component remains the same. Now it's very tempting to rotate these planes again to get a third set of cutting planes. This is almost perfect, but unfortunately not exactly perfect. We are now looking at 2 iterations and then it looks fine. However, after 9 iterations, the inaccuracy starts to become significant and grow each iteration after that. So just don't do this. If we have 2 planes, then they intersect into a line. Let's calculate the line of the 2 intersecting planes. We have a red and a green arrow representing the normals of the planes. The line is on both planes and therefore it is perpendicular to the normals of both planes. So we can instantly calculate the vector of the line by taking a cross product of the plane normal. That's the easy part. Now we need to find a point on that line. We are going to look perpendicular to the line to see what is going on. A plane has a single point that is the nearest to the origin. We can find that point by multiplying the normal vector of the plane by the distance of the plane. Now we can calculate distance u, and we can calculate distance v, and then we can calculate point P. And we can substitute u and v in to get a new formula. Now we have the line, so to get the grid point T, we must find the point on the line where it intersects the unit sphere. And that is the point on the line where its distance is 1 away from the origin. And remember to make sure to select the point that has a positive z value. And here's an overview of the formulas we created. Now that we have everything complete for a single triangle on the icosahedron, let's construct the full icosahedron. Surprisingly, we need only 2 values for that. We are going to call them u and v. U is half of L, and v is the value to reach a point 1 away from the origin using u. Now just plug in values u and v in the order as we are showing now. Great, now we have all the vertices of the icosahedron. Now let's turn this into triangles by connecting the dots. Here are the indices of the icosahedron. And that's a full icosahedron. Now we have the grid on a single triangle and we want to turn that into a complete sphere. Remember that we have been working with a system oriented like this. We will call this the global triangle. Now each individual triangle has its own local coordinate system and we will call this a local triangle. Each triangle has its own points A, B and C. We break down the system into 3 unit vectors and we call them vector x, vector y and vector z. A set of 3 local vectors is called a triad. We can easily calculate these vectors. Vector x is the unit vector of the line A to the midpoint between B and C. Vector y is the unit vector of the line from B to C. And vector z is the cross product of x and y. Whenever we have a point in the global system, we can convert that to a point on the local system. Let's call the global point G and the local point L. To go from G to L, it's the sum of x scaled by the x component of G, it's y scaled by the y component of G, and vector z times the z component of G. In reverse, to get G, the x component is L dot x, the y component is L dot y, and the z component is L dot z. It's that simple. Now that we have a complete grid, let's give each point in that grid a number. That's called indexing. To do so, we unfold the grid and we twist and tweak it so that it turns into 10 squares. Each square consists of 2 of the icosahedron triangles. In this case, we have done 2 iterations, so every square is cut into 16 squares. Each square is a grid cell, and each grid cell consists of 2 triangles. We give each point a number, and the index at the top left of each square is also the index of the grid cell. When we do that, we will eventually have 2 points more than we have grid cells. We are going to put the numbers 0 to 15 in the top red square. The next 15 points go into the next red square. And then we do the orange squares, the yellow, the green, then the blue ones. In the end, we'll add the last 2 grid points, starting with the top right and ending with the bottom left point. This is super convenient for computers to store information in the form of 10 square images. As a reminder, it is possible to calculate each grid cell in multiple ways, depending on where on the grid, at least 3 ways. Make sure to be consistent in how to calculate a grid point. If you calculate it with different slicing planes, you will get a slightly different answer. And that's it. As a recap, we have learned how to use vector operators, how to calculate the base points of the grid, 4 tricks to calculate the slicing points in 2D and the steps to apply them. That we should sort the slicing points by the x components, how to create a plane from a slicing point, how to calculate the grid points, how to build the icosahedron, how to turn a grid into a full sphere, and the way we index the grid. If you have come this far, you have learned how to construct a near-perfect geodesic grid, and I hope it is helpful. I might make another video in the future on how to turn this into a filled 3D grid. Thank you for watching.